This is the second video on the Green's function for the Laplacian. We're going to be looking at Green's functions for the Laplacian and for the gradient. In the last video, we derived the Green's function for the Laplacian. So we have our problem is del squared f equals g. G is our forcing function. Del squared is our Laplacian. We seek a solution. F of x is the convolution with our Green's function and our forcing function over all space. And we require that this convolution is equivalent to requiring that the Laplacian of the Green's function has the behavior of a delta function. And we found the specific form of the Green's function for the Laplacian, which is g of x prime is minus 1 over 4 pi times 1 over the absolute value of the difference of x and x prime. In this video, what we're going to do is we're going to verify that this is the case. We're just going to apply it to a test problem, like the finding the potential from the charge density in an electromagnetic field, and then verify that the Laplacian. So this statement here, saying that the Laplacian of the Green's function is a delta function, means that the Laplacian of the Green's function is everywhere 0 except at the origin. So we're going to verify that that's the case. And then we're going to verify the case that if we integrate strictly around an infinitesimal unit ball around the origin, we do recover our original function. So let's go ahead and do these. So first off, we have rewrite it once for reference. Let's go and take the derivative. So what is the gradient of this guy, or the mth component of the gradient? So d dxm dm of, and I'm going to focus here just on this term. I don't care about the minus 1 over 4 pi. We're going to find that we have that the Laplacian of this is 0, so the Laplacian of minus 1 over 4 pi times that will also be 0. Let's go and compute that. So d dxm of xn minus xn prime, all squared. We have the sum over all of these n's to the minus 1/2. That is the derivative we want to take. I don't think it actually buys us anything to use the abbreviated notation. So let's say just ddxm. Let's compute this to start with. We're going to want to take the second derivative of similar terms in the end. But if we do this, we get, by chain rule, minus 1/2 times 2 times the derivative of d dxm of xn minus xn prime, all times. So we have a minus 1/2 here. Minus 1/2 minus 1 is minus 3/2. So that means we have a 1 over x minus x prime cubed. And the derivative is just of this. So we compute this derivative. That is just xm. No, it's a delta. So we have minus delta mn. And that's why I'm hesitating, because there's a mistake here. This is the derivative times xn minus xn prime. So delta mn xn minus xn prime over x minus x prime cubed And summarizing, we have grad 1 over x minus x prime has to be minus x minus x prime, all divided by the magnitude of x minus x prime cubed. All right, there's one thing. Next up, we want the divergence of this. So if we want to compute, and notice here, specifically, that this is only true when x minus x prime is not equal to 0, because if that was the case, we'd be dividing by 0. So we're only looking at the case where x minus x prime is non-zero. So del squared of 1 over x minus x prime is grad dotted with the gradient of x minus x prime. And we just computed this piece. And if we look at that, so we have grad dot, I'll take the minus out, x minus x prime all over x minus x prime cubed. Okay. And we can do this in 2 steps. So we have grad dot x minus x prime all over x minus x prime cubed minus x minus x prime dotted with grad of 1 over x minus x prime cubed. This is del squared of 1 over x minus x prime. Grad dotted with x minus x prime is just going to be 3, because we're going to pick up a component for each x. So if we write that out in coordinates, we have em times d dx m dotted with xn minus xn prime en. We pick up only the m equals n components, and for each one of those we get a factor of 1, so that is 3. So just ignore that for now. So we have minus 3 over x minus x prime cubed, and we want to compute this part. All right, let's do that. Could have done this in less steps if we had thought of computing x minus x prime to the n beforehand, but we didn't. We did it for n equals 1, and so let's do it in this case for n equals 3 specifically. So we have minus 3 halves times 2 times delta, skipping steps here, but we're going to have, you can just write it out, dvx m of xn minus xn prime squared minus 3 halves and this is in the EM direction. And this part is, and I've already factored, I'll take out the 2 here. Skip too many steps. Okay, so we have EM times minus 3 halves times 2 times delta mn x n minus xn prime, which is just, and all over 1 over x minus x prime this time to the fifth. So we have minus 3 x minus x prime all over x minus x prime to the fifth. And that was grad of 1 over x minus x prime cubed. So if we put all our pieces together, we have del squared of 1 over x minus x prime is minus 3 over x minus x prime cubed minus x minus x prime dotted with minus 3 x minus x prime all right, so minuses obliterate each other, and we are left with minus 3 over x minus x prime cubed plus 3 x minus x prime squared over x minus x prime to the fifth. And provided that x minus x prime is not equal to 0, we have 0. Okay, so grad squared of 1 over x minus x prime equals 0 for all x not equal to x prime. So we just found the Laplacian of minus 1 over 4 pi 1 over x minus x prime equals 0 for all x minus not equal to x prime. We want to look at this behavior near the origin, and we want to see that Laplacian near the origin recovers our delta function behavior. And we can do that by introducing a test function. So if we have del squared f equals g, that has solution, f of x equals g of x prime, g of x prime dv prime, which is minus 1 over 4 pi and we found we want to apply the Laplacian now to this. So if we do that, we should recover g of x. And let's see how that's the case. So if we do this, first we see that the Laplacian only applies to x minus x prime because g is a function of x prime, and we're integrating over the x prime coordinates. So we've got here minus 1 over 4 pi del squared 1 over x minus x prime all times g of x prime. Now we've also found that this is 0 everywhere that x is not equal to x prime. So we can restrict our volume to a little itty bitty x minus x prime absolute less than epsilon, where epsilon going to 0. So now, if epsilon is going to 0, so x minus x prime is effectively the same point. So our g of x prime, we pull out of the integral, that's just going to be g of x. And this is all non-rigorous, but we really just want to get an idea of how this ends up working out. So now we're integrating over this epsilon sized sphere around the origin of, if we have a point x, we have a unit sphere, a epsilon radius sphere and these points here are points x prime. We're taking all points x prime in an epsilon-sized sphere around the point x. That is what we're doing. And we're now going to look at what is the value of this integral over that volume. This whole thing is del squared of f of x. Now, we can look at this part and say, well, the grad squared of 1 over x minus x prime is the same thing as taking the gradient with respect to the x prime coordinate, because if we swap x minus x prime in here, the absolute value is unchanged. So we take the gradient with respect to x prime instead. And now to look at that. It should be obvious why we want to do this, because we want to be able to apply the divergence theorem and turn this into a surface integral. And specifically, we have a surface that has volume of epsilon 4 pi epsilon squared. That's the area of this surface. So we change this from a volume integral into a surface integral. We get, well, before we do that, so g of x over 4 pi of grad prime dotted with grad prime 1 over x minus x prime dv prime. Now this is in the form that we can apply the divergence theorem, and we get minus g of x 4 pi of n hat prime dotted with grad prime of 1 over x minus x prime, and our dA is epsilon squared d sigma, where sigma is the area element, not area element, epsilon squared d omega is the area element, the solid angle. So omega is the solid angle, and epsilon squared is the radius squared. And what is our n hat prime? So our circle, our sphere, we have points x prime on the outside and points x on the inside. X not x prime. And our unit normal is x prime minus x over x prime minus x, which is minus x prime over the absolute value of x minus x prime. How about our gradient? We found that the gradient of 1 over x minus x prime was minus x minus x prime over x minus x prime. So if we take the gradient with respect to the prime coordinates, we're going to flip the sign, and that's what we'll get. So now we have n hat prime dotted with grad prime 1 over x minus x prime is, and that is a third. So n hat prime dotted with grad prime of x minus x prime is minus x minus x prime squared over the absolute value of x minus x prime to the fourth. And x minus x prime to the absolute value is epsilon. So that is minus 1 over epsilon squared. Nice. We've got del squared f of x equals minus 1 4 pi g of x times minus 1 over epsilon squared times epsilon squared 4 times 4 pi. 4 pi epsilon squared is the total area. And what do you know? Our 4 pi's cancel, our epsilons cancel, and our minuses cancel, and we are left with del squared f of x equals g of x, which is another way of writing that grad squared g of x prime is the delta function of x minus x prime. Cool. So there's a kind of non-rigorous proof that all of the contour integrals and other change of variables and tricks that we did last time, we never lost any signs or screwed up in any other way. We managed to find the right answer for the Green's function, and this demonstrates that's the Green's function. It's worth giving a little application. So the applications are almost trivial, but let's say electromagnetism. We have the Laplacian of our scalar potential is rho over epsilon naught. So how can we can now just go ahead and write that the scalar potential is minus 1 over 4 pi 1 over x minus x prime minus rho of x prime over epsilon naught dv prime. And what do you know? You have 1 over 4 pi rho of x prime dv prime over x minus x prime. We have our famous result from electrostatics, obtained the very long way